In the last video, we saw that our attempt to build the shortest path from S to D one edge at a time by following a greedy strategy failed. This kind of greedy strategy did not work in yielding the shortest path from S to D. But we know that there can be multiple different greedy algorithms. We saw in the minimum spanning tree problem, for example, that we had two different greedy algorithms that we looked at. In fact, there are more than that, but we looked at two of them and both of them worked correctly. So maybe there is some other way to be greedy which might work for this problem. So let's explore some other options here. What we want to do is to search for optimal substructure, because if there is optimal substructure, then we might be able to build a greedy algorithm which exploits that optimal substructure. Well, what do we mean by optimal substructure? Well, recall in the minimum spanning tree problem that if you are given a minimum spanning tree, and if we focus on a local region, any local region of that minimum spanning tree, and if we find that we can improve, if we can reconnect the vertices in that local region in a different way so as to improve the cost of that local region, then that local improvement would result in our improving the global minimum spanning tree, which should be impossible if what we had originally was already the minimum spanning tree. So we had optimal substructure in the minimum spanning tree problem. We said that any local region of any local structure of the minimum spanning tree must itself be optimal, must itself have been connected in a way that we have the lowest cost connectivity among the vertices in that local region. So is there something like that which applies to this particular problem, the problem of computing the single source shortest paths? Well, let's see. Suppose we have the shortest path from S to D laid down like this. Can we look at a local region? Let's say I look at this local stretch over here. Let's say this stretch begins with an X here and it ends with a Y here. If I ask the question, is this local stretch itself optimal? What would you say? So basically I'm asking whether this local path from X to Y is itself optimal or not. If the entire path is optimal from S to D, then it must be the case that this section from X to Y must also be optimal, because if it wasn't optimal, if there was a cheaper way to get from X to Y, then I could start from S, I could follow this path up to X, I could follow that cheaper way to get from X to Y, and then continue on till I reach D, and I would have a path that was of a lower cost than the shortest path from S to D, which was given to me at the beginning. Now that's clearly impossible to do, which means that any local section of an optimal path from S to D or to any other vertex must also be optimal, because if it was not optimal, then by making that local stretch optimal, we would end up improving the overall path from S to D, which is impossible to do. Now I'm going to focus specifically on local regions that are prefixes of the path. So if I start from S and if I just look at this prefix, the first two nodes, I know that this section must be the shortest path from S to, let's say, this vertex V1, because if it wasn't, then I could take a shortcut from S to V1 and thereby improve the overall path from S to D. By the same argument, if I look at this particular prefix from S to V2, even that must be the shortest path from S to V2. If I look at this local region from S to V3, that must be the shortest way to get from S to V3. So any prefix of the shortest path from S to D, let's say we're looking at a prefix from S to any vertex X, any such prefix must also be optimal. It must also be the shortest path from S to the endpoint of that local section. So what this means for us is because of there being optimal substructure in this shortest path, if we want to construct the shortest path from S to D, we have to first build the shortest path from S to V1 first, then build the shortest path from S to V2, then we have to build the shortest path from S to V3, then the shortest path from S to X, and only then can we build the shortest path from S to D. So we have to first build shortest paths from S to all the intermediate nodes before we can build up the shortest path from S to D. So that means we want to build shortest paths from S in increasing order of length. Now we really don't know what are the intermediate nodes between S and D because we don't know where D lies. So by default we will try to build shortest paths from S to every vertex in the graph in increasing order of length, and hopefully there will come a time when we hit D, and that is the moment when we'll know that we now have the shortest path from S to D built. So we want to do something like this. We'll start from S, then we will build the shortest path from S to its closest neighbor, whatever that is. And when I say closest neighbor, I mean closest neighbor in terms of the costs on the edges up to that neighbor. So it obviously has to be a one hop neighbor, because if there were multiple hops to this neighbor, then those intermediate nodes along that multi-hop path would be closer to S than this vertex itself. So obviously the closest vertex has to be a one hop neighbor. But the second closest neighbor of S might be a direct neighbor, or it could be the neighbor of a neighbor, of a previously close neighbor. So in this way we want to reach out to the neighbors in increasing order of distance. So let's say this was the closest neighbor, let's say this was the second closest neighbor, this was the third closest neighbor, and then we'll find the fourth closest neighbor. Maybe it lies somewhere here, maybe the fifth closest neighbor is this one, maybe the sixth closest neighbor is this one, maybe the seventh closest neighbor is this one, maybe the eighth closest neighbor is this one, and so on. So we want to basically build out this shortest path tree. The shortest path tree is a tree that we want to build which show the shortest path distances from S to every node in the graph. And maybe somewhere down here below we might find that there is a node called D, and in that case the sum of the weights of all the edges along the path from S down to D would be the length of the shortest path to D. But notice that there cannot be any cycles in the shortest path tree because no shortest path has cycles, as we've seen earlier. Moreover, we want to span every single vertex that is reachable from S. Every vertex that is reachable from S will have a well-defined shortest path to it from S, and so it must be included into this tree at some point. Now this shortest path tree is not that different from the BFS tree that we had built in the live class and the pre-class videos. In the BFS tree, the level number of each vertex was giving us the length of the shortest path from the source to that vertex, because each edge had the same weight, the same implicit weight. Whereas here the level number is not going to provide us that information, because the number of hops does not necessarily match the length of the shortest path. But in principle we are trying to do the same thing that we did in BFS, which was to start from the source node and imagine that there is this virus, this viral infection which is spreading out from the source at a uniform rate in all directions, and each vertex is going to fall sick on a specific day, which is going to be the day that corresponds to its shortest path length from the source. And so as each vertex falls sick, it gets included into this shortest path tree, because the shortest path would be known once it falls sick, and we just keep doing that in increasing order of shortest path lengths, and at the end the vertex that is farthest from S would be the last one to be included in the shortest path tree. So we have another greedy strategy now that we might try, which is to start from the source vertex and to repeatedly add the next closest vertex to the growing shortest path tree out of the source vertex. So we are not building up one single path out of S. We are actually building this shortest path tree, one edge at a time, one vertex at a time, exactly that the way in which we built the BFS tree, the way in which we built the DFS tree, and also the minimum spanning tree when we used Prim's algorithm. So we want to follow the same general graph traversal algorithm to start from the given source vertex S and to repeatedly incorporate into this growing structure one more vertex until we have all the reachable vertices from S included as part of this growing tree, which we're going to call as the shortest path tree. So this is actually the fourth type of tree that we will be building by following a general graph traversal strategy. The first two were BFS and DFS trees, and then in the previous problem we saw how to use Prim's algorithm to build the minimum spanning tree. Now the minimum spanning tree did not exactly look like a rooted tree, but conceptually, even though it wasn't, in terms of implementation, we did start from an arbitrary vertex as the source, and we picked, for example, vertex 0 as the source, and we repeatedly added the lowest cost edge on the cut to this growing structure, which ended up becoming the minimum spanning tree that was rooted at vertex 0. Even though we didn't look at it as a rooted tree, we could have drawn it as a rooted tree, just like we drew the BFS and DFS trees as rooted trees. Now in this particular problem though, the source is clearly given, so we know what the root of the shortest path tree is going to be, just like we knew the root when we were doing breadth first search to figure out the shortest path from a given source to all other vertices.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today